if we remember back to our linear momentum, P equals mv, and we think about an angular counterpart to that equation, a rotational version of that equation, that would give us an angular momentum. Angular momentum, we use a capital L, and instead of m, instead of our linear inertia, we would need a rotational inertia, I, and instead of v, a linear velocity, we would need a rotational or angular velocity, omega. L equals I omega. So an object that's rotating has angular momentum. And with linear momentum, we said that as long as there were no external forces acting on our system, the momentum had to be constant. It was the same at all times. It was the same before and after a collision. So we used momentum conservation. And we can say the same thing for our angular momentum L, that it's going to be constant if we don't have any external torque acting on our system. So we're going to use this to solve problems where we have things colliding in a rotational way. So let's do a quick example. So in this example, we have two disks that are rotating independent of one another. Disk 1 is above disk 2. Disk 1 is rotating as we look down on the top of it in the clockwise direction, and disk 2 is rotating in the counterclockwise direction. They're both solid disks, but they have different masses and different omegas. And what we're going to do is drop disk 1 down onto disk 2, and they're going to stick together and rotate together. And we want to know what's the final angular speed of the two disks as they rotate together after the collision. Two items are going to stick together, so we can't use energy. We know that we're going to lose some of our mechanical energy to heat, deformation, things like that when two objects stick together in a collision. So what do we use? We use momentum. In this case, angular momentum. We'll pick a positive direction. Actually, it's defined for us. Omega 1 was given as negative, and omega 2 was given as positive. So as we look down on the system, counterclockwise is our positive direction. What is L? It's I omega. So initially we have L1 initial plus L2 initial. At the end they're stuck together. For a solid disk, I is 1/2 mr squared. And when two objects stick together and move together, we can just add up the inertia of each of the individual objects. It's the same with linear inertia, right? M. If you're pulling a wagon and it's got a bunch of stuff in it, and you want to know the mass, the total mass, you add up all the masses of the stuff inside the wagon, and you've got it. In this case, you want to know the total rotational inertia of two objects that have stuck together. You just find each individual one and add them up. So this is going to be I1 plus I2. And since R1 and R2 are the same, I'm just calling everything R. Now we can solve for omega final. And now we have omega final in radians per second. It's just like the way we would solve linear momentum problems. You look at the momentum of each object before, in this case it's angular momentum, I omega. Afterwards they've stuck together, and we look at the momentum at the end, and we set them equal because it's an isolated system. As far as torque is concerned, there's no external torque acting on our system. As a simple example, let's look at a balance, or a teeter-totter maybe when you were a kid. We've got a board horizontal, there's a pivot point in the middle, and it's in equilibrium right now. It's not rotating. And we're going to drop something down, a little ball of clay. And if we drop it right over the pivot point, it ends up sticking to our board right here. And what happens to our board? Does it rotate? In our initial condition, the clay ball comes down. In our final condition, it's stuck to the board, but the board is not rotating. It can't cause it to rotate because it hits it right at the axis of rotation. So at the end, there's no rotation. At the beginning, there was no rotation. The wad of clay, the ball of clay hit it, and at the end, there's no rotation. Even after the clay hits it, there's no rotation. It can't get it rotating if it hits it right at the axis of rotation. So at the end, what's the angular momentum? 0. There's no rotation. And since the initial angular momentum is going to equal the final angular momentum, and the initial angular momentum for the clay plus the initial angular momentum for our balance or our board, and our board was not rotating, was it? So that means that the initial angular momentum for the clay had to be 0. And you might think, well, it's just a point mass. We're treating the clay as a small lump. It's just basically a point mass moving in a straight line. It's dropping straight down to the board. How could it have angular momentum? This makes perfect sense. But before you get too comfortable with that, let's look at it again. Initially, the board is horizontal, no rotation. And we're going to put a lump of clay here and drop it straight down. And at the end, it's stuck here to the board. And what's happening? There's rotation at the end. The clay hits the board, causes it to rotate. So L final is not 0. This is an object that's rotating. It has to have angular momentum. So initially, we had the clay moving straight down toward the board, and the board was not moving, so it had 0 angular momentum. So now we're saying the initial angular momentum of the clay ball is not 0. It has to equal something, because at the end it caused the board to rotate. At the end there's angular momentum. So there had to be angular momentum at the beginning. Even though an object is moving in a straight line, it can have angular momentum if it can cause something to rotate. If it can't cause something to rotate, then its angular momentum is 0. So let's look at this a little more formally. What happens is, if there's an axis of rotation, and there was in this case, right, it was in the center. That's the axis of rotation. If the path would go through the axis of rotation, like in this case, then there's no angular momentum, even if it was coming this way. Or going up. If the path goes through the axis of rotation, if you extend the line of the velocity and it goes through the axis of rotation, the object has no angular momentum. And that was the case in our first problem here. The path went right through the axis of rotation, so the clay had no angular momentum initially, and it could not cause the system to rotate. It couldn't change the angular momentum of the system. So let's take a look now at one that's not passing through. There's our axis of rotation. What we do is we extend the line of the velocity or the momentum, and we find the perpendicular distance to the axis of rotation, sort of like with torque in a lever arm. That's our perpendicular, and this object has momentum mv, and so what we end up with is the momentum multiplied by r perpendicular, and that's always the case. So let's take a look at a different example. We've got a board that can rotate and something that's coming this way. Extend that line. You find the perpendicular distance. Call that r perpendicular. And you can see that r perpendicular goes to 0 when the path of the particle goes through the axis of rotation. So we really have two formulas for angular momentum. For objects that are rotating, we use I omega, and for objects that are moving in a straight line, we use mv r perpendicular. Let's do a simple problem with angular momentum conservation where one of our objects is moving in a straight line initially. Let's do this example. A kid on a playground runs toward a merry-go-round, jumps, lands on the merry-go-round, grabs onto it, and causes it to spin. Maybe you remember these from when you were a kid. Initially, the merry-go-round is stationary, and the kid is running toward it, and afterwards, the system, the kid plus the merry-go-round, are rotating with some speed, omega final. Given this information, and the fact that the merry-go-round can be treated as a solid disk, let's see if we can find this answer using angular momentum conservation. So I guess I should make a point here. Both linear momentum and angular momentum could be used in the same problem. The reason I'm not using linear momentum here is because, as is typical in most rotation problems, the merry-go-round is pinned to the earth through its axis of rotation. Typically, when things rotate, they have an axle attaching them to something. In this case, the axis of rotation is attached to the earth. So the merry-go-round is attached to the earth. So when the kid jumps onto the merry-go-round's attached to the earth, you can't use linear momentum conservation. But the merry-go-round's free to rotate, so we can use angular momentum conservation here. If the merry-go-round was on a frictionless surface, and the kid was sliding along on the frictionless surface and grabbed onto the merry-go-round, then we could use both angular momentum and linear momentum to solve that problem. But in this case, because there's an axle pinning the merry-go-round to the earth, you cannot use linear momentum. Luckily, angular momentum still works. I'm going to call clockwise my positive direction. So initially, I've got the angular momentum of the kid plus the angular momentum of the merry-go-round. And at the end, I've got the angular momentum kid plus merry-go-round. The merry-go-round is not moving initially. It has 0 angular momentum. And the kid is moving in a straight line. So I'm going to say it's the mass times the velocity times r perpendicular. And at the end, it's I of the system times omega final. R perpendicular is just the radius of the merry-go-round. I of the kid plus merry-go-round is going to be I of the kid plus I merry-go-round. And if the kid is small compared to the merry-go-round, it's almost like a point mass. What's I for a point mass? mr squared. I for a solid disk, ½ mr squared. Now we can plug in some numbers and solve for omega final. So when I plug in the numbers, I get 0.286 radians per second for the final angular speed of the merry-go-round plus kid system.